Hi and welcome to part 2 of my series of presentations about the best methods to acylate alcohols for the preparation of carboxylic esters. This video is about the use of other electrophiles than acyl halides such as anhydrides, vinyl esters, imidazolides and other esters. At the end, there will also be some examples of enantioselective acylations that can be used to prepare enantiomerically enriched esters or alcohols. Carboxylic anhydrides, especially acetic anhydride, are among the most common electrophiles used for esterifications. In the presence of an excess of a weak base, such as methyl imidazole, anhydrides react about 10 times more slowly than acyl chlorides, as shown here. With DMAP as catalyst, this difference shrinks still further. One important advantage of anhydrides, if compared to acyl chlorides, is that anhydrides do not form mixed anhydrides with carboxylic acids as readily as acyl chlorides do. Furthermore, less reactive acylating reagents than acyl halides are better suited for selective monoacylations of polyols. Cyclic anhydrides are much less reactive than open-chain anhydrides. For example, no reaction occurs if a concentrated solution of phthalic anhydride and ethanol is stirred at room temperature for 1 hour. To bring about this reaction, either catalytic amounts of an acid or a base or a higher reaction temperature are required. In the second equation on this slide, a secondary alcohol was esterified by phthalic anhydride upon heating to 115 degrees Celsius for 15 hours without any solvent. Because the products of these reactions are acids, such reactions are autocatalyzed and potentially dangerous. A better control can be achieved by adding one of the reactants slowly to the reaction mixture at the same rate as the reaction proceeds. This here is an example of a typical acetylation with acetic anhydride. The only catalyst was acetic acid, but stronger acids such as sulfuric acid, zinc chloride or montmorillonite are more commonly used. Also bases may serve as catalysts, but these will be neutralized as the reaction proceeds. Some bases, however, still retain some catalytic activity despite protonation by acetic acid. The tertiary hydroxyl group of the starting triol in this example underwent elimination, but this can be avoided if milder reaction conditions are chosen. Here, for instance, the use of only 0.2% of zinc chloride as catalyst and a lower reaction temperature yielded terzbutyl acetate as the main product. Imidazolides are also readily available, stable electrophiles suitable for the acylation of alcohols. Imidazolides are not usually isolated, but prepared by mixing a carboxylic acid with carbonyl diimidazole just before adding the alcohol. It is also possible to add carbonyl diimidazole to a mixture of an acid and an alcohol, and esterification may occur even without the addition of a base. The example on this slide is such an in situ activation, but more examples can be found in part 3 of this video playlist, where I discuss various reagents suitable for the in situ activation of carboxylic acids. This is an example of esterification with isolated benzoyl imidazole. The reactivity of imidazolides can be enhanced by protonation, and here pyridinium triflate was used as auxiliary acid. Pyridinium hydrochloride or sulfate would probably also have worked. When a non-symmetrical diol has to be monoacylated, selectivity can often be improved by using an acylating reagent of low reactivity, as shown here, even if these less reactive electrophiles require a higher reaction temperature and longer reaction times. Pivaluyl chloride, the strongest electrophile in this comparison, yielded about 25% of the unwanted diester. With the less reactive pivalic anhydride, the resulting product mixture only contained 11% of diester. Finally, a pivaluyl thiazolene brought about a selectivity of 96:4 without the use of any auxiliary base. If a given electrophile is too unreactive, esterifications can be accelerated by partial or complete deprotonation of the alcohol with a strong base. In this example, the cleavage of an acyl oxazolidinone was achieved by treatment with magnesium methoxide in methanol at 15 degrees Celsius. As mentioned in part 1 of this video playlist, vinyl acetate is prepared on a large scale as monomer and is therefore readily available and inexpensive. Vinyl esters are about twice as reactive as phenyl esters. In this example, methyl lactate was acetylated with vinyl acetate, and as basic catalyst 1.5% of potassium cyanide was used. Before performing such reactions, one should also consider that as byproduct the highly flammable and reactive acetaldehyde is formed. Like formaldehyde, acetaldehyde readily alkylates electron-rich arenes and undergoes quick aldol condensations. Tertiary alcohols do not readily react with vinyl esters, but this reaction can be catalyzed by samarium complexes and oxime esters, as shown here. The authors claimed that only the simultaneous use of both catalysts provided for a complete esterification of the alcohol at room temperature. N-hydroxysuccinimidyl esters are also electrophiles of moderate reactivity only and will react with tertiary alcohols only in the presence of strong bases or some catalyst. In this example, a mixture of DMAP and scandium triflate was used to acylate a tertiary alcohol with Bock-protected phenylalanine. Transesterification is a further important strategy for the acylation of alcohols. Catalysts and procedures have been developed that allow such reactions to proceed under acidic, neutral or basic conditions, and I'll show you examples of each of them. Most transesterifications are conducted under basic conditions, as in the example on this slide. Because methanol is more acidic than menthol, the reaction proceeded almost to completion with only one equivalent of methyl cinnamate as electrophile. If the acidities of the two alcohols are similar, though, an excess of one of the reagents will often be required. Another strategy for shifting the equilibrium toward the desired ester is distillative removal of one of the products. In this example, instead of an allylic alcohol, the corresponding acetate was transesterified with methyl palmitate. Methyl acetate, which boils almost 10 Kelvin lower than methanol and has also a lower enthalpy of evaporation, was continually removed by distillation. A number of catalysts have been developed which enable transesterifications to proceed under nearly neutral conditions. These are particularly well suited for base or acid-sensitive alcohols or esters as those of this example. Here, a titanium alkoxide and a large excess of alcohol were used, and the expected new ester was obtained in 71% yield. In this example, the ester electrophile was used in excess, and only 5% of a heterocyclic carbene was sufficient to bring about the acetylation of benzhydrol at room temperature in only 1 hour. Meldrum acid and related esterified ketone or aldehyde hydrates are cleaved to vinyl esters at about 100 degrees Celsius and can be used to acylate alcohols under neutral conditions. The scope of these reactions is low, but for some synthetically useful intermediates this is the best strategy. This here is an example of the use of an acidic ion exchange resin as transesterification catalyst. In this instance, ethyl hexanol was formulated with an excess of ethyl formate. Catalysis by bases would be less convenient here because formates usually decompose into carbon monoxide in the presence of bases. Lactones are often prepared by acid-catalyzed cyclization of hydroxyesters, as in this example. Here, 12% of toluene sulfonic acid was used as catalyst, and the lactonization required heating, but often these reactions already proceed at room temperature at acceptable rates. Another electrophilic acylating reagent of moderate reactivity are trichloromethyl ketones. In this example, catalysis by sodium ethoxide was required. Because chloroform is also generated, these reactions do not always proceed cleanly, and the product may contain dichlorocarbene-derived byproducts. A number of strategies enable the enantioselective acylation of racemic alcohols with anhydrides or vinyl esters. There are some synthetic catalysts, as the one shown here, that can achieve remarkably high enantioselectivities and yields. Much better results, however, are usually attained with immobilized lipases, as in the next example. The most common catalyst for enantioselective esterifications is Candida antarctica lipase immobilized on a polymetacrylate resin. This catalyst is compatible with organic, even hydrophobic solvents, and can also be used at higher temperature, as in this example. Here, both the newly formed ester as well as the unreacted starting alcohol were obtained with an extremely high enantiomeric excess and an almost quantitative yield. In this example, the lipase-mediated enantioselective esterification was combined with ruthenium-catalyzed racemization of the unreacted secondary alcohol. This led to a complete consumption of the starting alcohol and a high yield of only one enantiomerically enriched ester. So, what are the potential side reactions? When using vinyl esters as acylating reagents, besides all the byproducts that may result from acetaldehyde, certain catalysts can cause the formation of vinyl ethers from the starting alcohol. This is, however, only rarely seen, but the released acetaldehyde can be a real issue because of its high reactivity and flammability. When sulfuric acid or sulfonic acids are used as catalysts, substantial amounts of dialkyl sulfates or sulfonic acid esters are sometimes formed as byproducts. These are potential mutagens and must not be present in intermediates for food, personal care, or pharmaceutical products. In the presence of strong acids, even weak acylating agents can acylate electron-rich arenes or alkenes. One extreme case would be the formation of beryllium salts from isobutene and acetic anhydride. But even under milder reaction conditions, such acylations at carbon may occur to a small extent and cause the formation of annoying impurities. On this and the next two slides there are some further, mostly recent examples. This reference list can also be found in the description of this video. The next presentation is about the acylation of alcohols with carboxylic acids activated in situ. Because carboxylic acids are more stable and less expensive than electrophilic acid derivatives, in situ activation is a very popular strategy for the acylation of alcohols. So don't miss it.